Hello and welcome to the talk on distributed and parallel low diameter decompositions for arbitrary and restricted graphs. This is joint work together with Jinpeng Do, Henning Hillebrand, Christian Scheidler, and Julian Wertmann. Now let us begin this talk by untangling this unwieldy title and answer the natural question of what are low diameter decompositions. Now, for a low diameter decomposition, we first consider a weighted graph G. Furthermore, we assume that the graph is undirected. In this presentation, I will only use unweighted graphs, but all the techniques I present to you will also work on weighted graphs as well. I just use unweighted graphs for an easier presentation. Now, given such unweighted graphs and a parameter d, in a low diameter decomposition, we are looking for a set of connected subgraphs of G such that all of these subgraphs have a diameter of at most d. Let me give you an example. You see these four subgraphs here marked in red, blue, and green. All are connected and have a diameter of at most 4. In the sense that from every node in the red subgraphs, you can reach every other node in the red subgraphs in at most 4 hops. Now, since all of these hops are contained in the red subgraph as well, we say this is a low diameter decomposition with strong diameter 4. In contrast with the weak diameter, we would also be allowed to use edges which are not part of the subgraph to get to the desired diameter. But throughout this talk, in the paper, we only talk about graphs of strong diameter. Now, if the only restriction is that these subgraphs must be connected and have a strong diameter of d, I can give you a very trivial algorithm that can compute you a low diameter decompositions for every possible parameter d. Namely, we just say every node is its own subgraph. Then trivially, these subgraphs would have a diameter of 0, which is lower than any d imaginable, and they also would be connected since there's only one node in them. So in order to make the problem non-trivial, we need additional restrictions. And in particular, what we want is that we want as few edges as possible to be cut between the subgraphs. And by cut, we mean that one endpoint of an edge is in one subgraph and another endpoint is in another subgraph. So here in this example, we have 5 edges that are cut between the subgraphs, namely 3 up here, which are between the red subgraph and the blue subgraphs, 1 down here between the red and the green, and 1 here on the right side between the green and the blue. Now, there are several flavors of low diameter decomposition that count the edges that are cut between subgraphs in a different way. In this talk and in the paper, we assume so-called probabilistic low diameter decomposition. That means for every edge of length L, we want that the probability that this edge is cut between subgraphs to be an O of some factor alpha times the length of the edge divided by d. You can see this formula down here. So that means the longer the edge is, the more likely it is cut between the subgraphs. And since we want to have the edges be cut with a low probability, our goal is to find like a very small factor of alpha that minimizes this probability. Clearly, we cannot go below alpha equal to 1, because in that case, the probability that an edge is cut is just the edge of the length of the edge divided by d. And if the edge is longer than d, it must be cut because the diameter of the connecting components can only be d. Now, as you can maybe imagine, these low diameter decomposition are a useful tool if you devise divide and conquer algorithms, because you can subdivide your graph into these small subgraphs and then separately solve the problems in these subgraphs. And since this is so useful, there have been many previous works which already have considered these low diameter decompositions. In particular, it is known that if you have an arbitrary graph, so you know nothing about the graph, so the topology is not restricted in any way, the best possible quality, so the best possible value of alpha, is O of log n. So you cannot be better than that if you know nothing about the graph. However, if you have a subgraph of a restricted topology, better low diameter decompositions are possible. So for example, if your graph has a bounded tree width, so that means your graph is very, very close to being a tree, then the best possible quality alpha is not the logarithm of n, but the logarithm of this tree with tau. So for example, if you have a tree, that would just be some constant. Or if you have a graph which is very close to being a tree, it would be the logarithm of some small constant. So this is like very, very good. Similarly, if you have planar graph, also the best possible value of alpha is a constant. So it's just O of 1. More generally, if the graph has a bounded genus, so it can be embedded into a surface of genus G, then the best possible quality is the logarithm of the genus. And most generally, if your graph excludes a fixed minor kr, so very roughly speaking, your graph cannot be reduced to a clique of r nodes, then the best possible value of alpha is this O of r. Now, all of these algorithms you see here are designed for the classical sequential model. That means we have a processor, the graph is stored in the memory, and one edge or one node at a time can be accessed. However, this paradigm of low diameter decomposition is also very useful for parallel algorithms and also for distributed algorithms. So we are interested in bringing these algorithms to the parallel and distributed world. Now, some efforts have been done if the graphs are unweighted. For unweighted graphs, essentially, there are distributed algorithms out there that match these bounds. However, for the weighted case, these things are not so clear. And this is why in this talk, in the paper, we ask ourselves the question, can we find better distributed and parallel algorithms for low diameter decompositions in weighted graphs? And seeing that I give you this talk, the answer is yes. So our results can be divided into two groups. First, we have a result that holds for general graph. So for a general graph, we show that for any parameter d, we can compute a low diameter decomposition with a strong diameter d and a quality, so a value of alpha, of O of log n. That means for every possible value of d, we can basically produce the best possible low diameter decomposition. And also our runtimes, our algorithms can be implemented in a lot of models, and in all these models, the runtimes are quite competitive. So for example, in the contrast model, the runtime for the whole thing is O tilde of HD plus square root of n. Here, HD denotes the hop diameter of the graph. So the length of the longest shortest path between two nodes if we ignore the weights. So roughly speaking, this is the time a broadcast would take in the contrast network, which is like a natural lower bound for this problem. So this is for contrast and on a general graph, this is quite fast. Unfortunately, due to the time restrictions on this talk here, I cannot go into the details of all the models, but trust me when I say that this is fast. It essentially matches the runtime of the previous best algorithms. Furthermore, our algorithm can also be implemented in the novel hybrid model. In the hybrid model, nodes can not only communicate with their direct neighbors in the graph, but also can send messages to essentially any node in the system. However, the number of messages they can send is limited to O of log n. In this case, surprisingly, the dependency on the hop diameter falls away, and it is simply possible in a polylogarithmic time. Oh yeah, I forgot to mention, this O tilde hides polylogarithmic factors. And finally, in the PRAM, so in a parallel model, we can implement our algorithm in polylogarithmic depth and quasi-linear time in the number of edges of the graph, which is also as fast as the best previously known algorithm. So for general graphs, we have a quite good result, although it's only a small step forward compared to the last best known result. Basically, in the last known result by Becker, Lenzen, and Emek, they produced graphs with a weak diameter, and with essentially the same runtimes in all of these models, and we just turned that into a strong diameter using like a little tweak on the algorithm. Much more interestingly, our techniques can also be applied to these restricted graph classes I talked about before. So what we do is we do not present a dedicated algorithm for planar graphs, graph of bounded tree width, and so on, but instead we present an algorithm for like a meta class of graphs, which can then be applied for all these graph classes I listed on before. And this meta graph class, let's call it, are so-called k-path separable graphs. So what do I mean by that? So probably most of you will know what a separator is, but for the sake of completeness, let me give you a very short intuitive definition. So let's consider the graph from before. And we notice that in this graph we had from before, if we remove two shortest passes from this graph, the remaining connected components will contain at most a constant fraction of the nodes from the original graph. So you'll recall this graph here from the beginning. It's like a subset of a grid graph. And if we remove this red part here, red path here, and this blue path here, we can see that the remaining connected components of the graph are far smaller than the original graph. So the set here on the left side only has 6 nodes. The set up here only has 3 nodes, and the set here only has 4 nodes. And then again, in these subsets, we can again find a small set of short passes such that if we remove them, the graph will even then fall into smaller pieces. So intuitively, a graph is k path separable if I remove k shortest passes from the graph, the size of the remaining connected components is at most half the size of the original graph. And furthermore, in these connected components, I can again find k shortest passes to decompose them even further into smaller parts. The full definition is a bit more complex than that. You can find it in the paper. But for the purpose of this talk, simply think we can remove k passes from the graph, and then all the remaining connected components are small. And as it turns out, for all the graph classes I mentioned before, they all fall into this class of k-path separable graphs. So clearly, any graph that you can imagine is n-path separable. You can always basically remove all the nodes and be done with it. If your graph have a bounded tree width of tau, it is known that this is tau plus 1 separable, because you can always find a set of tau plus 1 nodes that separate the graph, and each of these nodes is the shortest path to itself. A bit more complex, every planar graph is 4-path separable. That means you can remove 4 of the paths, 4 shortest passes, and you fall into smaller components. If your genus is G, you must remove O of G shortest passes. And finally, if you exclude KR as minor, then there are F of R many passes that you need to remove. Now, this F of R simply means this is a function that only depends on R and not on N. So if R is a constant, this function is also a constant. However, the actual value is quite large. It depends on this Seymour-Robertson theorem, and it's like something in the magnitude of 2 to the 2 to the 2 to the R to the 1000. So it's a really large constant, but nevertheless, as R is constant, it's a constant. And more precisely, what we show is if our graph is k-path separable, so if it's any of the graphs I just mentioned, then for any parameter d, we can compute a low diameter decomposition with strong diameter d and a quality alpha of log k plus log n. So if we think about k as something that is constant, or at least polylogarithmic, we have a complexity of log n. So we have like a exponential improvement compared to the general graphs. And also the runtimes are very competitive. In the contrast model, we have a runtime O tilde of k times the hop diameter. So this additional square root of n is gone. And again, in the hybrid model, we have a runtime of O of k. So if k is constant or polylogarithmic, the whole thing is polylogarithmic. And in the PRAM, we have the depth of O tilde of k and work that is polylogarithmic in k and n. So again, very good runtimes. Now, if you compare this with the sequential algorithms, we see the following. So for general graphs, we achieve the same quality as the best known sequential algorithm, which is very good. But even for these restricted graph classes, as we can see, the best known alpha in the sequential world is log of tau. For graphs with tree with tau, we have log of tau plus log n. For planar graphs, the best known is O of 1 in the sequential world. We have log n. For genus graphs, it's log g versus log g plus log n. So for all these graphs, the price that we pay if we run this in a parallel and distributed world, and therefore much faster than in the sequential world, is this additional log n, which is not much, but still dependent on n. But we hope to get rid of this in future work. So we have reason to believe that this log n can be taken out. The situation is a bit more complex for graphs that exclude a fixed minor. There, the best known alpha in the sequential world is O of R, where we have log of this f of R. So even if we get rid of the log n, this log of f of R is still magnitudes larger than O of R. So here a bit more work needs to be done. So this is an overview of our results. And so the natural question is, how do we do it? So as you can see, our algorithm can be implemented in a lot of models, and I cannot go into all the details, but I try to give you the rough ideas, high level of how we do it. So let's first start with general arbitrary graphs. So as mentioned before, the result here is basically a small refinement of the algorithm of the algorithm for LDDs with a big diameter that was presented by Becker, Lenzen, and Emek 5 years ago. So what we do is we combine it with some techniques that are known from LDDs for sequential models, and simply generalize the algorithm a bit and also make it work for strong diameters using some small observations that we can make along the way. So the main technical theorem is that if you consider a graph G, and suppose we have done like a bit of pre-processing, namely that we have identified or marked a set of nodes X such that for the set X, two properties hold. On the one hand, for each node, at least one of these marked nodes is in distance at most d. So every node has a marked node close to it. And second, there are at most tau of these nodes in distance 3D. So that means not too many nodes are close to it. Then from these two techniques alone, we can construct a low diameter decomposition of strong diameter 6D and quality O of log tau. So this sounds a bit technical, but it will prove very useful later. So for example, if you have a general graph, you can always say, I can mark all the nodes. Then definitely you have at least one node in distance d, namely the node itself, and at most n nodes in distance 3D, because, well, at most all the nodes can be in that distance. So using that, we can compute an LDD of strong diameter and quality log n. And just as the algorithm of Becker, Lenzen, and Emek, this can all be done with like some approximate shortest path computations, which can be done in all the models that I mentioned. This is simply just a refinement of their ideas using some mathematical insight. So it's really just an epsilon improvement compared to their algorithm. It's really just taking their work and tying up some loose ends. The more interesting thing is, of course, the algorithm for the k-path separable graphs. And in the remainder of this talk, I try to give you the rough idea of how that one works. So the main idea is the following. So we start with our graph of n vertices. The first thing we do is we use our general low diameter decomposition algorithm to reduce the diameter of that graph to d times log n squared. So we just take the algorithm we developed for general graphs, we run it on there with like a slightly higher d, and make sure that all the connected components of the graph have a diameter of at most d times log n to the square. We just do that. We just always make sure that our diameter is very close to the diameter that we actually want for our subgraphs. What we then do is we compute the k-path separator. So that means we compute a separator that consists of O of k approximate shortest passes. So since we reduced the diameter of the connected components before, we can also tell that the length of these approximate shortest passes is also at most d times log n to the square. So because we reduced the diameter before. So we have k passes of length d times log n square. What we do then is, on each of these passes, we mark a subset of nodes such that all of these nodes are in distance roughly d to one another. So in a sense, we build like a d net or an independent set with distance d on each pass. The result is that since the passes are of length d times log n square, there are at most log n square marked nodes per pass. And since they're at most k passes, they are k times log squared n, many marked nodes. And now we take these marked nodes and put them into this framework I showed before. So that means we use these nodes as the set of marked nodes x. Now, since there are at most k times log n squared marked nodes, there can at most be k times log n squared marked nodes in distance d. And for all the nodes which have at least one of these nodes in distance d, we can put them into the right subgraph. Of course, that may not be all the nodes, because only the nodes that are really close to the separators can be put into a subgraph in a step. However, we can show that at least half the nodes get clustered in every step. So then on the remaining graph, we just do the same thing again. We again shrink the graph to have a small diameter, we compute the separator, and we compute our subgraphs from the separator. And then, step by step, there are at most log-n iterations of this, because in every iteration, the subgraphs shrink by a constant size. And therefore, using the general lemma we shown before, we get the LDD that we need. However, all of these steps only work under the premise that we can compute this k-pass separator. And here comes in the difficult part, because these k-pass separators are, depending on the graph class, quite difficult to compute. Now, if we have a planar graph, one can essentially extend known path separator construction algorithms to the congest model and the hybrid model and simply use them. So there's an algorithm by Ghaffari and Pata, which computes path separators or planar graphs in the congest model. With some little adaptation, we can take that one. Or for example, for graphs of bounded tree width, there are also quite fast algorithms that compute like this tree decompositions for these graphs, and based on the tree decomposition, it's easy to arrive at a path separator. So for these graphs, we can kind of just do it. However, if the graph has a bounded genus, excludes a fixed minor, or is in some other way only k-path separable, there's simply no known algorithm that can be easily computed, that can be easily implemented in the distributed and parallel world. Simply, we are not aware of one. And to say that now, we do not really develop one. So we were not able to devise an algorithm that computes a proper k-path separator in the distributed and parallel setting in the runtime that we want to have. However, we do something not just as good would be the wrong thing, but something good enough. Because recall that in every recursive step of the algorithm, we reduce the diameter again and again. So we make sure that the diameter is always at most d times log n squared. So that means we do not really need to compute a proper k-path separator, but it would be enough if we remove enough parts such that every node has at most a constant fraction of the nodes in distance d log n squared. Because then, if we do the shrinking, then all these nodes are not reachable anymore anyway. So instead of computing like a proper separator, we compute what we call a weak separator. And in fact, computing a weak separator is much, much easier. Because for that, we only need to compute a few approximate shortest passes. And in the remainder of the talk, I will give you the rough idea of how and why that works. So the idea is the following. So we consider a k-path separable graph with a bounded diameter of O tilde of d. So in this example here, we have a grid graph, which is one separable. Namely, it is separable by this red path here. The algorithm does not know this path. What we now do is we pick two nodes in distance O of d independently and uniformly at random and sample the path between them. So we pick a node v1, a node w1 in distance d, and pick the path in between them. Now, with a constant probability, the node v1 is on the left side of the grid, and the node w1 is in the right part of the grid. So with a constant probability, we cross the separator with that path. If we extend that to a general k-path separable graph, with a constant probability, the two endpoints of the path are in different connected components once we remove the separator. So with a constant probability, we sample a path that crosses the separator. So that means the paths that we sampled here and the separator, they share at least one node. That means if we put the blue path in our separator, we also contain one node of the original unknown separator. Now we could continue this and sample passes and like cover one node at a time. However, that would take a long time because the separators can consist of many nodes. So instead of just adding like the nodes that are on this path here, we also add all nodes in distance epsilon times d to this path. This epsilon is a tunable parameter that can make the separator a bit bigger, but also reduces our runtime. So by adding all these nodes that are close to this path also to the separator, we always make sure that whenever we sample a path that crosses the true separator, we cover a large chunk of the separator. And then add that to our weak separator. Now, once we have done that, we again sample two nodes uniformly at random and sample a path between them and thicken that path. And now our main insight is the following. So as long as the probability to cross the separator is like a constant, we will always remove like an epsilon fraction of the separator path with a constant probability. Once the probability that crossing the separator is below a constant, that means that most of the nodes will not have many nodes in distance d, because otherwise we would sample them with high probability. That means most of the nodes must be far away, so where they will be separated when we compute our big decomposition. And thus, by sampling roughly k random passes and thicken them up, we can find a weak separator, which is then enough to be put in the framework. So the takeaway message from this whole talk is essentially, if you can just sample paths uniformly at random, you get a weak separator, which you can then use in the construction of the low diameter decompositions. And with those words, I say thank you and hope you enjoyed the talk. And if you have any questions, feel free to write me an email or to talk to me at the conference. Okay, that sense, goodbye.